Okay, so as we left off on Tuesday, hopefully the winter weather didn't wash everything away from your memories. We were just wrapping up caches, and we wanted to come up with the metric that we would use to evaluate memory hierarchies. Right, so the right way to think about average memory access time is if I want to compare two different memory hierarchy options, right, whether it be just two single layer caches, or as we'll go later on in this class, some arbitrary, graph of caches connected to each other in some way, right? What you're ultimately worrying about is their impact on the average memory access time. That's how you're going to say whether a given memory system is doing a good job or not. Okay. Now, AMAT can be a little bit tricky in that it does not directly relate to CPI, in that you can actually have higher AMAT and still technically actually get better performance if you, for instance, are getting stuff that is covered. Your L1 hit rate, say, for instance, is covered by N pipeline stages. Well, your AMAT will go up, but your CPI might stay the same. So it's not a direct plug-in for CPI, but it's still a good proxy for most of the comparisons we'd want to do between memory systems. It is an average. So when we look at this in a little more detail, when we remember that even our simplest system we were looking at in like a 331 processor had two caches, has an I cache and a D cache. So you do need to specify, are you talking about the average memory access time for just the I cache, just the D cache, or all of them? Right, again, your average instruction does about 1.3 memory operations, right? So again, this is also going to get factored in there, and you'll take the appropriate average. Okay, but we'll come back to this after we finish diving all the way through all the optimizations we've done to the data path. We go deep dive in the memory system. Okay, so let's switch gears briefly. And it's not going to make for a very exciting portion of the video because I'm switching to a different machine. But let's see if this is more legible this time. So join on into your Kahoot. It's not going to be the most immediately topical. It is from the review deck. So again, don't worry too much about the particulars on this one. This is still a bit of a format check. The question we'll be doing at the end of this deck, because we'll pause in the middle of the sequence of questions, will be relevant to what we talk about later today. Okay, we're getting there. So for logistical ease, I will try to. Okay, I believe that one of your names is unlikely. Hey, for logistical ease, I will try to put these up at the beginning of all the lectures so that we can overlap the logins before class even starts. Did things start a little slow today? Okay, I think that's probably about all of us. Anyone still attempting to open a web communication device? Good enough. Let's get started. So the short version of this is that it doesn't seem to be a way to make the actual quiz question visible, but I can put a slide in front of it that has all the information in a size that is not ridiculous. We can pause here for an appropriate amount of time and then move on to the quiz question. So again, this is not immediately topical for the cache we're just talking about. This is again a format check. Can this be read in the back? That is the highlight of this. Good, okay. So again, lots of different design space options. If you're looking at things that are actually still around today, register memory like x86, where your operands can come from either registers or memory. All of the RISC style designs are register-register. They're load store machines. It's another name for the same thing. Stack machines still around in the JVM, and accumulators, well, unless you have a really cheap calculator, not so much in existence anymore. But they did have their time. And in particular, if you look at this question here, consider an alternate universe, say, the 1950s, where registers and internal storage in general were incredibly expensive and memory is fast relative to compute. Which ISA would these people possibly have been using? Right. So if you were, banging around on the ENIAC and the JOHNNIAC and all these other vacuum tube machines, right, that were substantially larger than this platform here that I'm standing on. Also, fun fact: JOHNNIAC had another name. It was called the computer that was afraid of the dark. You ever go visit the Computer History Museum? You can go find out why. Short version: vacuum tubes are actually photosensitive. Yeah. Okay, so now we'll move on. And we'll do the actual quiz question, which is just basically doing one of those options in the small form. I'll remind you what each of them is, but even though you can't read this, hopefully you were able to read the previous slide. Okay. Again, also, other than today, we won't usually be doing these at the beginning of class. So we'll show the login at the beginning of the class, but we won't actually do questions at the beginning of class because, well, people still got to show up, right? And you got to have enough time to slip and fall on your tuchus and on the icy sidewalk, right? Okay. Well, I didn't say they were good designs, but they were designed that you could afford. So as I was sort of trying to allude there with my mention of all those old machines were accumulators because they could only afford one register. Right, that was it. That was the whole budget. So think old school calculator. Okay. Also a note to do try to be consistent with your naming, but also have your name be something you're willing to have seen by people. Okay. So same setup, but we have something universe much more like our own, where memory is incredibly slow compared to registers and compute. What would you use? Right, technology marches on. Nothing else new on this slide. Everything else is the same, other than we are changing that condition. And we will, before jumping in to vote on the next one, feel free to talk to your neighbors for about 30 seconds or so. All right, talk this one over. So compare, contrast, and pure learning do actually tend to work, at least the pedagogy tells us. So speak amongst yourselves. Right? Is this going to change the answer relative to the previous slide? Yes, obviously the answer to that is yes. The only question is how. Well, actually, that's I think there's a bug here. Should have been reg. So you were all right, and entered in. I clicked the wrong button on which one was correct. So this one isn't terrible, but this is even better. So either the yellow or green was reasonable. Yeah. Okay. Again, we're not too worried about anything other than the format check for this one. Okay, great. So we'll pause here and we'll come back to this after some actual new material. Great. We can read it. Everyone knows what pure instruction is. Life continues. Okay. Okay, so we're going to look at understanding program dependencies and how that goes to a general sense of scheduling. So we're going to start thinking outside that box of our. No, it'll go away eventually. Okay, we're going to start thinking outside the box of our simple 5-stage pipeline. We're going to think about general program schedules and things we can do to make the schedule better. There. Not sure why that is not minimizing, but well, we'll live with it. You're going to lose your slide titles for a little bit. So when we talk about program dependencies, we're really talking about either data or control dependencies. Data dependencies are the simplest to think about. I have a producer, I have a consumer, right? I as the operand, right? For my input, something that's produced by somebody else, I have a dependence. Great. It's not the only type of dependence I might be worried about, though. Right? So for instance, if this is the instruction that's going to send the signal to launch the nuclear weapons, there is a dependence, it is a control dependence on actually reaching that code. Right? It would be nice if that instruction only executed when the conditions leading to it actually happened to be true. Right? So there can be causal or side effect reasons, or even about visibility of exception handling, for instance, or the need to synchronize among multiple concurrent computations that are going to lead to additional ordering dependencies, right? Everything ultimately is about ordering. Your instruction is, your program is trillions of instructions long. They don't all happen at once. They happen in some sequence. Can we understand what the constraints on the possible sequencing of these instructions could be? And in particular, you want to think about two different types of dependence. Some dependencies are very concrete, right? So if I have add, C equals A plus B, and following immediately by, D equals C plus E, right? That second one is always dependent on the first, right? Let's say I have a store and then a load. There might be a dependence. Depends on where in memory you stored the data and where in memory I'm loading from. And if those addresses are dynamically computed, I may not even be able to tell you, certainly without a lot of complex analysis, whether or not those could possibly be dependent. Right? So maybe I'm storing to a offset of 0 from a register and then immediately load from an offset of not 0 from the same register. I can tell you those aren't dependent. There's no dependence through memory. Right? But if I just load from two different registers, I would now have to prove that those registers do not actually have the same value at that time in the program ever, which sometimes you can do, but often you cannot. Right? So sometimes you have maybe dependencies, sometimes you have dependencies which are conditional on control behavior. Right? So let's say I define A to have one value in one branch of an if else. I define A to have a different value in the other side of the if else. Which one do I depend on? Right? I might depend on either. Right? Dynamically, I'm going to depend on one or the other. But if you're looking at the analysis of the program itself, right, there are two potential dependencies, one of which will actually be realized at runtime. And of course, you can think of these at all sorts of scales, right? This is not something unique to instructions. Programs can depend on each other. Functions can depend on each other. We can have things that are indirectly dependent through memory state, right? And so the way that you are then going to think about all of these sequencing constraints together is something you'd call a program dependence graph. All right, so the set of all of the constraints among all of the, excuse me, all of the instructions in your program. Right now, if you think about the static form of your program, right, so just the instructions that live in your binary, this is a general directed graph, right? Your programs have loops, they have all sorts of interesting structures. If you're looking at the actual execution of the program, assuming your program is correct, it's not fundamentally flawed, it should be a directed acyclic graph. You do not want cycles in your dependencies among your dynamic executing instructions. That makes no logical sense. That's going to deadlock and it's never going to resolve. Something very strange has happened there. Okay. So why do we care so much about sequencing? So, well, it turns out causality is kind of important, right? In fact, everything that we build all of our logic on top of has some fairly strong causal assumptions. Some of these are built into the models of the ISA. Right, so we'll talk more about this when we talk about different memory models you could have. So for instance, there are different models about the orders that events could possibly have happened under concurrency. And those will be baked into your ISA, right? They'll have different strengths of ordering among concurrent events. But you have to make a choice, right? You have to have some particular model. Otherwise, you can't reason about causality, and then you can't write parallel programs, and or you could, they just wouldn't work, right? It's not really clear what you'd want to even say about an operation unproduced data even means. And thinking about this in terms of graphs is also pretty useful, because this is to some level really how the compilers and the hardware view, I'm anthropomorphizing, but view programs for optimization, right? And some of the things that we're going to look at here, we're going to look today mostly at this from a software perspective, but we're going to end up doing in hardware some of these same things, obviously with very different resources at runtime in nanoseconds than the compiler has, but some of the same goals. Okay. Now, as we hopefully recall from Tuesday, when you think about our pipelines, the presence of these dependencies impose some fundamental limitations on how fast and efficiently we can execute. Right. So if you had no dependencies, if you just had a straightforward flow of instructions, then I could pipeline that really, really, really deeply. There aren't any backwards loops in my pipeline. I don't need a lot of hazard checking control. Everything scales very nicely, right? But that's not the world we get to live in, right? So everywhere that there is a loop in that design. So there's actually a paper. This is the title of that paper from somewhere between 20 and 25 years ago. Obviously, the illusion is back to World War II. Loose loops sink ships. The loose loops sink chips. But the same general idea is that everywhere that there are loops in your pipeline, these are very problematic. And so if you look at designing the actual data path, right, you have to design under the understanding that these dependencies are going to screw you up. And you need to make the potential places they could do that as limited as possible. Okay, so there's stalls. Control dependence limits your ability to understand what will execute. If I have some enormous, big straight line piece of code, right, then I don't have maybe dependencies. I only have definite dependencies, right? If I have no control, I don't have a very interesting program, right? But if I have no control at all, or at least I have no control for a very, 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 very long run, I can build a static schedule that will respect all these dependencies very nicely. It's not a very hard problem. If I have an arbitrarily twisty, a maze of twisty branches all alike, also cave reference there, then understanding the set of possible worlds you could be in is an exponential explosion. Exponential explosion, go combinatorics. And optimizing across that becomes quite a bit more difficult. So you have to do so conservatively. Conversely, the other way to look at this is when we look at a dependence graph, we're actually in some sense less concerned about the dependencies than finding things that are independent. So if in the dependence graph, there are no dependencies, I have enormous opportunity, right? All of the things that we did basically between the mid late 1980s up through even really the early 2000s were mostly about transparently exploiting naturally occurring independence, or otherwise trying to amplify the amount of independence that we could get in order to exploit that with a larger hardware budget. Right. So the other way to think about this is, what does more transistors give you? Gives you hardware parallelism, gives you throughput. Right. Doesn't do anything for latency of a single instruction. More transistors does not make one instruction faster. There are ways you can figure out how to do that, but it's hard. There's a lot of effort. You have to be clever. Right. But more transistors very naturally gets you more things in parallel. More transistors, more switch in parallel. You have to find all that parallelism. Right. So what are we actually looking at when we talk about that? Okay, so let's just make sure we're all on the same page with nomenclature. So our instructions are going to be our nodes in our dependence graph. And you can think about instructions without too much loss of generality as having one or more operators, 0 or more operands. Right? Yes, there are no ops. We're not going to worry too much about scheduling no ops. They'll do fine more or less no matter where you put them. And this differentiation between operators and instruction, right? They're pretty much the same thing in a RISC ISA, because every instruction does pretty much only one thing, right? If you think about CISC ISAs, certainly a given instruction may have several operations that it actually performs. So these are not necessarily exactly a one-to-one mapping, right? So with respect to instructions, what we care about are the resource dependencies. So are my input and output resource locations alive? Are they valid? Right. So for instance, if I'm doing add into register 2 the contents of register 1 and register 5, I need a valid copy of 1 and 5, and I'm locking down register 2 until I have executed, and so no one else can be using register 2 until I've done that, and any subsequent consumers have also consumed it. Right, so there's subsequent consumers, data dependencies, and then control dependencies. Right, under what particular paths does this instruction get executed at all? Right, so this is about the resources it needs, who it needs to be consuming from and producing to, and does it actually execute at all? So the next level of granularity that is of interest is a basic block. Right, so a basic block is a single entry, single exit run of instructions. So again, when we say a run of instructions, I'm presupposing some potentially unnecessary linearization, but without loss of generality. It is a contiguous set of co-control dependent instructions, right? So these are all a set of instructions that will either execute 1 or 0 times based on whether the basic block is executed 1 or 0 times, right? Since it's single entry and single exit, I hit everything that's in there on the way through, right? So within a basic block, there is no control flow. It is a straight run of instructions. Yes? Maybe, right? So let's say I have a loop, and let's say my loop is C of I equals A of I plus B of I, for I, right? That would turn into a single basic block as the body of that loop. There's no control in C of I equals A of I plus B of I. But I could have a body of a loop that certainly has control, right? So I could have the body of my loop be if A of I greater than 0, C of I plus 0, right? So you can get down to the next one. So the next level up. So basic blocks are sort of a ubiquitous unit that's a little more useful to think about when you think about control flow graphs. Right, so within a basic block, there's no control, so I can collapse this down and not worry about instruction to instruction to instruction to instruction, right? And then just reason about the flow across basic blocks, and since that's these are all sort of entailed. It's a little bit an easier graph to look at. Hyperblocks are a DAG of basic blocks. So hyperblock is a feed-forward set of basic blocks. So these actually often are what certainly your innermost loop is often a hyperblock, right? So there are no loops in the hyperblock. So now the difference between a hyperblock and a basic block, again, other than the fact that a hyperblock is a set of basic blocks, any given instruction in a hyperblock, when a hyperblock is executed, will be executed exactly 0 or 1 times, right? When a basic block is executed exactly once, if the basic block is executed, 0 otherwise. Here, right, I could have my if-else. It's all forward flow. There's no loop. It's a useful unit for thinking about optimization and potential dependencies and parallelism, right? Because if I want to look at, say, for instance, code motion or moving things around, the resource entanglement is quite different if you're moving across a loop boundary or not. Right? If you're looking at multiple versions of something across loop iterations that you're trying to dynamically create versus saying moving something that happens to be independent before or after an if, right? That might be perfectly legal. Right? I have some completely independent computation, maybe my I++, right? I could do just as well before or after my if-else. Hyperblock will capture that level of structure. Okay, loops and loop nests. So this is just a very specific class of cyclic program subgraph. Yes. No. So let me give you a quick example here, right? So if these are basic blocks, right? So this is some standard if-else construct. I don't have to tell you exactly what instructions are in here, but I have some condition computation, right, which leads to a control instruction, which is going to take me on either one of these 2 paths, and they both have a join after. So I see this diamond, I think, if-else, right? This whole thing is one hyperblock composed of 4 basic blocks. Obviously, on any particular path through, not everything gets executed, right? But nothing in there gets executed more than once, right? So hyperblock is a DAG of basic blocks, no loops. Okay. Loops are special, not just because, well, they finally actually might have an instruction execute more than once, but they're also special because they're incredibly common. So the reason we bother to name them as something of interest is most of your time is spent in some loop nest somewhere. Right? This is where most of your time goes in your program. So it's worth bothering to think about. They're also actually fairly regular, right? In particular, if I have, for I equals 1 to 1,000,000, right? There are a lot of things I can actually optimize about that. I know to a great degree what is going to happen structurally, right? If I have some complex condition on my while loop, right? So, while f of x, right? Understanding how that's going to evolve as a function of time is a little challenging. So different types of loops do structure a bit differently and can be optimized a little bit differently. But a lot of them do have a nice, very simple structure. In fact, if you go all the way down to you have an innermost loop, and the only thing in there is a basic block, and it has a fixed finite boundary, that is just screaming out for SIMD, i.e. vector instructions, to come and optimize the heck out of that innermost loop. There are lots of things you can do. Okay, functions, procedures, again, these are reasonably common. Again, functions are nice because they have a nice narrow interface of a single point of entry, any number of exits, any number of loops or loop nests within them. Hardware exploitation of arbitrary functions is hard in a different way than loops. So loops aren't just going to optimize by compilers. Actually, even the hardware will sometimes recognize that you're in a loop there are things called loop caches, right? So it'll actually have like a level 0 cache that detects that you keep executing the same instructions over and over and over again and tries to feed them more rapidly. They're fun things that you can do, right? So a loop is about as complex a thing as hardware can really, to some degree understand. Hardware can understand that you called a function or returned from one, but what the structure of the function is, the hardware is never going to figure out, right? So this is purely really useful for compiler level. But the interfaces there are also interesting because, again, you can look at things where the dispatch of the execution of some other piece of code with a well-defined point of entry and a well-defined protocol for returning is a way you can start looking at things that operate in distributed models, even if you're moving computation around on chip. You can go even further up and talk about objects of compilation. We're not going to really worry about that, but this is just the unit of compilation and binary generation. And optimizing across these is, well, harder. Okay, so if you look at then an actual execution, right? Let's say you have the static structure of a program, right? You've got some function main. It definitely calls foo, bar, and baz. Bar definitely calls garply. Baz definitely calls qux, which calls itself some number of times, some recursive function. And foo may or may not conditioned on control, if else, called garply. And garply does a dynamic dispatch to some unknown function. It's got some function pointer. Is it going to be this one? Is it going to be this one? We don't know. So all we know is the type. That's data dependent, right? Can't be analyzed statically. And then any given particular execution, right, is some path through this. In this case, foo didn't call garply, but garply happened to call this particular function, and qux recursed, down 3 layers. Okay. We can zoom into, one of these functions, say, and look at again the same static versus dynamic view of control. So we zoom in from the outside in into basic blocks. Again, each of these is going to have 1 or more instructions, right? There's no limit on the number of instructions you could have in a basic block. In practice, they're fairly small, right? The average basic block size in branching integer code is like 5 instructions. A floating point might be closer to 10. But you can get particularly long or even single instruction basic blocks, right? It varies a bit. But even at this level, you can start to understand some structure, even though I show you no code at all, right? So here you have an if, not an if else, just an if, right? And you have it leaving the function entirely. Here you have a loop. This is probably some sort of head, and this is some sort of loop tail, which then turns into this. Again, this is also an if, and here's an if else, right? Could it technically be some other code that created that? Sure, but these are the sort of natural patterns that you would pick up just from looking at static analysis. And then obviously dynamically, it's some path through here, right? If this is a data dependent loop, it's not a fixed n, right? Maybe it's a parameter of the function. Yes.
So if the static is fixed stuff, why is it called static?
Oh, so this is your static program binary, right? So this is not actively executing, and in your static binary, every instruction exists once, right? In your dynamic binary, I execute the contents of this some number of times, and some of these things aren't executed at all, right? Yeah. So the issue is that there are many possible dynamic executions that could come from the same static graph, right? And sometimes, right, they're pretty strongly entailed, right? Like maybe, as I said, maybe this is a fixed n. In which case, I know exactly what's going to execute here. I could even flatten this if I really, really wanted to, right? But in general, if you were able to know which direction all these branches were going to go, you wouldn't need branches, right? So there's always going to be some dynamic behavior, right? So in that same sense, as I said before, let's think about some instruction in basic block 6, right? And where it's going to get its input from. Right? Let's say it depends on some variable that is initialized here, but conditionally changed there. So which one is it dependent on? Right. Well, from the static analysis perspective, it has to respect the dependencies to both, because it could come after either. Right. So in terms of optimizations I can apply, that has a conservative constraint. Dynamically, it's either dependent on this or this. Right. One or the other happened. Button. Okay. And again, the types of dependencies we care about: raw, wa, war. Right. So read after write are the consumer produced consumers that produce operand, so standard producer consumer relationship. Right. These are the ones that you are sort of inherent to any plausible construction of your program in some sense. Right. There's some real dependency. There might be other ways to articulate it. There might be ways to optimize it out, right, if it happens to be redundant. But this is a real expressed dependency. There's no way I can understand the value of X if I have not yet understood the value of A, right? The other two are just fundamentally about resources. And again, if I get more transistors, I might be able to play games with my resources. If I get more transistors, I can't suddenly understand the value of X without the value of A. But here, I just want to reuse A. I want to reuse this resource. I want to assign something else to it. I cannot do that until all of the uses of the old version of A have been consumed. So if I move this across this, or if I try to do these both at the same time, right, I have some ambiguity about, well, which A am I talking about? Similarly here, right, you would not presumably see these immediately back to back. That would be a bit silly. Right? You can imagine that if this was A equals B plus C, A equals A plus Y, but otherwise there's presumably some code between these. But you have a write after write dependency. Again, I can't redefine the current value until all uses of the old one have actually occurred. Right? Okay. So hopefully you should be able to, again, visualize how these things are going to relate from real code to graphs. So here's a for loop, some if else, some join code here at the tail. Right? These are all going to be preserved in some level. But what we're going to be a little more interested in is thinking about this as it plays out finally now at the instruction level. Right? So this is a snapshot from an LVM IR. So it's not exactly MIPS, but it's pretty close to 3-address code other than these get element pointers, which would turn into multiple instructions in a RISC ISA, or they're just computing the address. So think of this as a straight line run of sort of things that are dependent on I and A. Okay, so you can think about all the different types of dependencies that you have, right? So there's a loop in here, right? And we're going to look at sort of all the potential dependencies, right? Going this way. So even across different sides of an if, let's draw those lines in. Right? These are things that we would have to respect from a perspective of optimization. And then I've noted here with these dashed lines, a loop carried dependence. Right? So in one execution of this loop, nothing to worry about here. If you're looking at multiple executions of this loop, you would have to obey the relationship between I and its next version of I. Same thing for write after write, same thing for write after read. Okay, now, how many of you have ever played around with compiler optimization passes? How many of you have ever bothered to compile a program? Oh, seriously, man, you should upgrade to PyPy, then at least it JITs. Okay, so a very, very common pre-optimization pass in, which here I'm a little annoyed that the screen share is blocking this. Let's see if I can. This is something called a single static assignment. Okay, now it goes away. Sometimes, you'd almost think that code might not always work. Okay. The single static assignment is a very, very important pre-optimization pass in most compilation flows. And what it has done, we'll talk about this new funky instruction here in just a second. What it has done is it has gotten rid of a lot of those previous arcs. And the way it has done that is it has basically said, look, the way that you write your code, you keep referring to variables and they're going to evolve over time. And we're going to talk about actually versions of variables a little bit. We're going to just use more names. Right. So we'll say that the A that you assigned on one side of an if and the A that you assigned on another, we'll just call them A0 and A1. And we can reason about them accordingly. Now, that is going to mean that you're going to have something that decides which version of something you're interested in. So think of this as a multiplexer. Right. So this is a way to turn a control dependence into a data dependence. Right. So the logic here is I1 will receive either the value of I or I2, depending on whether your predecessor basic block was basic block 0 or basic block 4. So depending on where you came from, right, in the control, we are going to produce the appropriate version of what I1 is. I1 could either have been initialized from here, where we set I to 0, or it could be the standard I++ coming through this loop. And the whole point of single in single static assignment is that you only have one instruction that defines the value of a name. Right? So SSA, you look across here, you'll note that the values that are being set don't repeat. Right? I never redefine a variable. So if I never redefine a variable, well, other than through looping, obviously, I'm technically getting some additional versions here. But in any straight line piece of code, I never redefine a variable. I'm going to have a different set of write after read and write after write relationships. But if I have renamed it correctly, right, other than a little bit of adjustment here through this fee instruction we added, all of our read after write dependencies are preserved. Okay, so let's flip back. Oh, silly. There we go. Okay. And let's go to the next question. How much were you listening to what I was just talking about for the last minute or so? Apparently the answer is you mostly weren't looking at your phones. Okay, I'll give you more time the next time I do a switch like that. Apparently it's there's a larger context switch overhead. So if we look at these different properties here, okay, so no variables ever assigned a new value is obviously false. Right? I mean, I keeps getting new values every time we go through a loop. Right? It does get new values. Right? There is dynamic flow. Right? There are no raw dependencies amongst multiple static instructions would be a very uninteresting program. Right? You still, as we just saw, have the raw dependencies. That's kind of the whole point. We did just use a whole bunch of new names because every version of something now is its own unique name. But what we will have given you is that there are no WA and WAR dependencies among static sets of instructions, which will enable you to reason about just the raw dependencies without worrying about these sort of artificial resource constraints until later, right? And while preserving all of the producer-consumer causality that makes your program actually your program. Now, this is a compiler optimization, but all of this is going to happen again in hardware. And it's going to actually be one of the biggest keys to unlocking a whole lot of performance in out-of-order execution. Right, so the way that we are actually going to start viewing our programs in hardware fairly soon, but after midterm 1, so for you in eternity, is going to be involving exactly this. Okay. So if you look at this set of operations, we can sort of reconstruct the program dependency graph. Right? Now, what I want you to think about in this program dependency graph versus this is linear. This has been linearized. I had to write them down in some order, right? The graph is not a stick, right? So if I look at this graph here, right, and I say, okay, 0 and 1, these two instructions are dependent. They are strongly ordered. What about instructions 2 and instructions 3? What is the relative ordering requirement between instruction 2 and instruction 3? Yes. Yeah, these are concurrent, right? They're not parallel, they're concurrent. They are not ordered, right? They don't have to happen at the same time. They just have no actual strict ordering dependency, right? They both have to come after 1. They both have to come before 6. Other than that, I can't tell you anything, right? And this is where is going to be mined for performance with more aggressive pipelines. Yes?
So the 2 and 3, is that like an if else, or is it like writing two things?
No, these are 2 address computations. Yeah, they're just, yeah. So,
Okay.
so the basic block boundaries are these orange, red, orange. They will both run. So everything in the basic block. So the control flow here, right? Okay, let's do it. So the control flow boxes are this sort of red-orange color. Everything in one of these boxes will co-execute if you reach that box, right? So the if-else is here, right? When you go from here to either 10 or 8. Right? I'm drawing some multiple granularities here at once. So we've exposed the internals of the basic blocks, right? And they have internal structure. So 2 and 3, it's nice. They have the same control dependencies. So any possible ordering of these is perfectly valid, right? Could have ordered them either way in that linearization. There's nothing, that needs to have done 2 before 3 or 3 before 2, right? So that's where you're going to get what we would call instruction level parallelism, right? That is a property of the underlying program, right? So if I have a program and I write it such that every instruction depends exactly on every previous other instruction transitively, you have no ILP. Nothing I do in hardware, asterisk, almost nothing I do in hardware is going to really help you, right? There are some things you can do if you're sufficiently speculative and clever, right? But it will turn out that most programs are not sticks. Most programs have some degree of inherent concurrent structure, right? Now, if all I'm getting is one instruction at a time from this, it's very hard to figure that out, right? So you're going to have to be a little more aggressive in looking for it, or someone's going to have to tell you, right? So if someone told me you can do 2 and 3 at once, then you could build hardware to act upon that instruction to do multiple things in parallel. If I am not told this, I would have to discover it. You can build hardware structures to check all of the dependencies, right? So there are a whole long history of different approaches to try to discover this. So for instance, you can go back to the 1960s, not necessarily with IBM. Have people ever heard of the CDC 6600? Central Data Control? No? Okay. So that used a technique called scoreboarding. They basically had a table of the dependencies and they looked up and checked whether you were dependent on anything else that was there. And if you weren't, great. You were independent and you were free to continue forward. Right. So lots of options. Note that those machines in the early 60s often did not do any sort of control speculation. They were just looking to exploit this. Right? Control speculation is a little harder. Right. So do the so what of all this, right? Again, you should help understand what optimizations are or are not possible and when, right? How much information would I need to be able to make some understanding of whether or not, say, 2 and 3 were in fact independent, right? That program graph doesn't come with your code. Your code is just a bunch of binary, right? That graph is gone. You can reconstruct it, some of it, right? But it's not actually shipped with your binary. Right, so some of this information is lost after code generation, right? Some of it is preserved, and understanding this in terms of a graph, or at least some portion of that larger graph, is where we will be playing around with all of these different optimizations or challenges therein. So for instance, memory dependence is very difficult to understand from that sort of graph. It tends to be too dynamic, right? And the compiler, here is another reason why hardware ends up doing a fair bit of work. The compiler can only do optimizations on the static graph, right? Because any optimization compiler has to do has to be valid for any possible execution of the program. Hardware actually doesn't have the same constraint, right? I only have to optimize and do something that is sound for the set of instructions I'm actually executing. So I can do different things in hardware on a dynamic trace through my program that would not be legal for all executions of the program, as long as they are legal for the execution I am currently observing. Yes?
What you're saying, compiler can only see a dynamic view?
No, can only see the static view. Yeah, compiler can only see the static view. You can look at things like profile guided optimization. So you can do a run on some test input and then use that information as a set of hints to the compiler as to which among multiple possible conservatively statically sound optimizations it wants to deploy. So let me give you a straightforward example. I have an if and an else. I have to linearize my code. So either the then or the else case is going to come immediately after the code I just executed. Right? It's going to be sort of straight line, a fetch of instructions. So if I can use the profile guided optimization to choose whether I do the then next or the else next based on which one of these is more common, because it happens to be more efficient to fetch a straight line of instructions than just as a caching optimization. Right? So those sorts of optimizations you can do with a profile guided optimization, but they're still sound. Right? Both of those are still correct. I haven't changed the correctness of my program. I'm just doing a performance optimization. The hardware will be able to do things that are not actually statically sound. Right? So it can, for instance, when we do register renaming in hardware, right? This is for a particular trace, not for any arbitrary execution of the program. Right? So the resource versioning it sees is the only one it has to deal with. Similarly, with memory reordering, hardware is going to be able to speculate and roll back. Well, speculating and roll back in software is challenging at that granularity. Okay, so we've been talking about ILP, that there are other forms of parallelism as well. And you really want to think about this as in some sort of ideal world where I could throw as much data path with as few constraints on it as possible, then my limit would become whatever the inherent instruction level parallelism of a program is. Right? So a given program has an inherent ILP. Right? That's a property of the program to a great degree. A program may also have data level parallelism. Right? So I said, if you have some simple innermost loop, screams out for SIMD. If I want to add 1 to every element of A from 1 to 100, right? There's not really any instruction level parallelism as currently written. Right? There's not much to do to be parallel within this loop in one iteration. But data-wise, I could do this for a bunch of elements in A in parallel. It'd be just fine. Right? But the way to turn your data level parallelism, something like this, or even into ILP, or to expose more ILP, is loop unrolling, which is what we're going to spend the remainder of the lecture on today. So let's say that this is your code example. Here's some really naively scheduled sequence of instructions. It's a simple loop, right? And let's say for the sake of argument, right, that this is more or less something like this, right? Something where you have some well-defined static boundaries. The bounds are fairly large, right? So it's not for I equals 1 to 2. So if you just look at this piece of code and you want to analyze it, hopefully you can already see some problems with what's been generated. If you want to run this on a 5-stage pipeline, in that there are going to be some stalls. But here are the dependencies, right? In red, you have the dependency between the load word and the add. In blue, between the add and the store. In green, between the add and the add I and the branch. Now, one important thing to think about: your compiler doesn't actually know that you're running on a 5-stage pipeline, at least in general. right? That is a microarchitectural non-exposed feature of your processor, right? So, you know, in some sense, you can't directly blame it for not observing that there will be exactly 2 stalls, right? Because there's another going to be exactly 2 stalls. This might run on a 20-stage pipeline. There'll be more than 2 stalls then, but yeah, it's 2, right? So if you know the pipeline, you can try to optimize around it and schedule for a particular ordering. But more broadly, what you can at least try to do is take everything that you know is dependent and push them further apart. Because no matter what your pipeline is, the further apart they are, the less likely that dependence is going to manifest as a hazard. So we can do better already without anything interesting. And for the moment, we're gonna ignore branch prediction, right? So if you schedule this on our default 5-stage pipeline, not so great, right? So your CPI running through here, you do 5 instructions with 2 stalls, 7/5. Not amazing. And if you do a little bit better, right? So if you move things around, you can fix that. You can move the add-I, you can recalculate the constants. Great, I've pushed my things as far apart as they can go, right? If I had a deeper pipeline, I'd probably still have stalls, but at least for my 5-stage, great, now I'm better. And what you want to think about here broadly, what I really want to optimize for is not, again, the execution of 5 instructions, but the execution of this entire loop, which is presumably some non-trivial portion of my execution. So can we go further? Yes, because there are more slides. Yes. It doesn't know the optimal ordering, but it has a set of sound heuristics. So move my dependent instructions as far apart from each other as they can be, right, is a good heuristic, right? So while preserving the original program semantics, push stuff further away that depends on other things, right? Yes. So that's part of the compilation. So the resource uses. So again, so if you want to look at again what the compiler view is here, this is an intermediate representation is what it's called. So your front end of your compiler generates something like this. So Clang, if you're familiar with that, that's the front end of that LVM tends to use. It produces some internal representation, which is not quite assembly code and certainly doesn't target a particular ISA. Going from this to this is the back end of a compiler code generation. Where probably some of these optimizations have actually already been done on the intermediate form before even going to CGO. But you can do these sort of small scale maneuverings of architecture specific resources even quite late in the lowering. Yeah, so there'll be usually some fairly late stage where it attempts to do scheduling optimizations that are, again, not pipeline specific because I don't know exactly what's going to run on, but that are pipeline specific oriented, right? So you can tell it prefer to use, something like an ARM, Cortex 57, right? We think you're going to run something like that, so you load that set of heuristics. But some of these are more general, right? So loop unrolling in particular actually would probably have been done even before we got into quite this level here. We'd still have get element pointers and such. Okay, so we're going to do some loop unrolling. Useful. So if we have some loop, and for instance, let's say it didn't have a whole lot of ILP, we might be able to extract more if we look at across iterations. But we can't do that easily because there's a branch in the way. But if you have something with structure like, for I to 100, I can reason about that branch, right? So let's say that I want to just, unroll it 4 times. So I have to still respect all the existing, dependencies that were there. If the loop bound is 0 mod 4, then this is easy, right? If it is actually, 100 iterations, then I don't have to add anything other than just doing it 4x. If it's 101 or some other thing, I can put some compensation code at the top that does the part that isn't 0 mod 3. Yes. No, this is well, okay. So there's a deeper answer to that in that people have done research on that. oh, what the heck is the name of the thing? Guri Sohi's work out of the early 1990s. Speculative multi-threading. No commercial device uses this. Lots of people have tried. So technically, yes, but in practice, no. We're still looking at optimization with a single thread of execution. Yes, they have independent sequencing. Yeah, yeah. So you can derive multi-threaded versions of something from that. So, for instance, a dual loop. That would be something like OpenMP. That's a different process, and we'll talk more about parallel computation once we get to more than one core. Yeah. Okay, so we're just going to unroll the loop to find more exploitable structure, right? We want a bigger graph to chew on, that hopefully we can find more things that are independent of each other. Okay, and we're gonna, use more names. So if we unroll it really naively, well, we eliminated 3 branch instructions and nothing else, right? This would be technically valid. It wouldn't be, very good. The only thing that would help us with is where we now have probably a reduced branch misprediction penalty. Not that this was difficult to predict in the first place. Right, so if you want to understand again at a loop level, if you even took that naive one that hadn't even been scheduled yet, and you went from 7/5 to 5.5. You went to 7 to 5.5. Obviously, we could do a little bit better. We could do the same thing we did before, right? We can reduce this further. In particular, we can figure out that compilers are smart enough to know that subtracting 4 repeatedly can be turned into subtracting 16. So we can get rid of a few more instructions. We do have to adjust all of our constants accordingly. And then again, we want to push everything as far away, producers and consumers, separate them like soccer fans, right? And once you've done that, right, you're going to need a lot more naming, right? Because previously you could just rewrite T0 repeatedly, just do it 4 times. Now you're going to need a few more registers. In this particular example, not too bad, right? I've got plenty of registers to name my 4 live variables. But if you look at architectures that were designed, which will be the focus of Tuesdays with VLIW, that were designed with a whole other loop unrolling and other compiler optimizations in mind, they do have a lot of registers. The Itanium had 128 registers, right, versus the MIPS 32 at the architectural level. For reasons like this, it only would work if you unrolled things very aggressively, so you need to have the additional names to play with. Okay, so just the constants, great. Right. So if you push all this together, we went from our basic loop, which was 5 cycles per iteration, and even on our scalar machine, right, just reducing the overheads here, and then fixing all of our dependence distances gets us down to 3.5 cycles per iteration. Plus, we've now got dependence distances that are much larger, right? So nothing is dependent on anything within 4 instructions. You could push this even further as you increase the factor of unrolling. Diminishing returns on here, right? We've already done most of what's going to happen there for redundancy elimination. Increasing returns on this, right? So if you're looking for a greater distance between dependencies and potentially exploiting that, right? That's where you're going to go. Okay. So a few minutes left. I will actually just bring in a second here. Give you a little foreshadowing of where we are going with this. We're not going to go too deep here, and we will start again from the beginning. Speaking of which, logistics, the Kaltura recordings are now linked in the modules, and these slides are up as well. And I put up a deeper dive on branch prediction as a set of additional review slides. So do take a look at that if you want to review branching a little bit more. We'll come back to branching in more depth when we need it more as we get to out of order superscalars. Okay, so where we're going with all this compiler stuff, you say, well, isn't this a computer architecture class? Well, there was a time, it was the 80s. There were a lot of things that were happening in the 80s, right? There was a time when an idea in computer architecture was that the compiler people were going to solve all of our problems for us. So it is useful to think about what tools they had available, right? The way that they were thinking about the problems before we look at what we actually went and did as we go and try to get more performance out of these machines. So we're just gonna stay on this slide for today. If I have a scalar, i.e. one wide, in order pipeline, like your FDEMW, or even an FDH, how many stages you put here, right? There's some fundamental limits. It's called the Flynn limit, right? You cannot get a CPI of better than 1, right? If you're only fetching 1 instruction per cycle, the most you could be completing is 1 instruction per cycle, right? It's kind of pretty straightforward. You can play around with your, and if you recall from the execution time equation, right? The 3 things you have control over are number of instructions, right, at the ISA level. So you could come up with new instructions that do more SIMD, and then you'll execute fewer instructions. Great. CPI is still stuck at, best 1, but your instruction might go down. You could do various, attempts to optimize the total number of instructions you have to deal with by getting better branch predictions, you have fewer waste instructions, et cetera. But those are pretty marginal. You can play a lot with the clock, and people certainly did. Right, your 286 is your 286 isn't even pipeline, but if you look at sort of the ramp up from a 486 at say 66 megahertz up through your early Pentiums, which were 100 up to even maybe 200 by some of the later ones. Right, you're getting 2, 3, 4x improvements in clock speed. The technology will keep getting your clock better. And in particular, if you pipeline deeper and deeper, you can even within the same technology get that clock speed up a bit, as long as you don't completely obliterate your CPI. So there's some challenges in doing this from a expense perspective, though, and we'll dive into this a little more in the deck right after this when we talk about hardware derived rather than compiler derived superscalar approaches. Which is that the amount of checking that you have to do is a function of your pipeline depth. There's some quadratics in there because you need these all-to-all checks. And your hardware budget may be going up, but your ability to actually fit everything within a clock cycle is still going to be subject to those quadratic constraints. Things aren't going to scale indefinitely, right? And diminishing returns, right? You spend more and more of your time just storing and retrieving data out of pipeline latches. At some point, as I said with the Pentium 4, right, you had entire stages where you did nothing but retrieve, move the data somewhere else, and store it again. Okay. The other way to get more out of your machine would be to fetch more than 1 instruction at once, right? If you want to get a CPI of on the other side of the Flynn limit, at some point you have to have a multi-fetch, multi-issue machine, right? So if you think about what this means for your best case, consider the following. Right, so if I have a 6 gigahertz 4-way multiple issue machine, I can fetch 4 instructions per cycle, right? My peak CPI goes down to 0.25, or again, when you start going from M1 Abrams gallons per mile to your Prius miles per gallon, you can flip your units here and talk about instructions per cycle of 4. Right. Now, there are a bunch of other things that are going to have to start to happen here as well. So if this machine somehow, and trust me, hit 6 gigahertz, you do not have a 5-stage pipeline. But just to make the math easy, if I had a 5-stage pipeline and the rest of this holds, how many instructions are in my pipeline at once? It'd be pretty easy. There are 4 instructions per cycle times 5 stages. There are 20. All right. Now I just told you the average size of a basic block is 5 instructions, and there are 20 active instructions in this pipeline. Right. So this is going to come back and be the source of a number of challenges. But we're going to sidestep all of them first and say, what if I still fetch one instruction at a time, but every one of my scare quote instructions is actually specifying several parallel operations? Right? What if I had an instruction, an ISA, that was actually the Cartesian product of my sort of RISC style ISA, right? So I might be able to say, here is a set of 3 parallel instructions that I'm going to treat as one bundle. And I already proved that they were parallel. So logically, they're basically one instruction marching down the pipeline, right? My compiler is going to prove all these things for me. It's going to schedule everything. Everything's going to scale. It's going to be beautiful. The fact that you're not using it means obviously something went wrong, but we will get to that on Tuesday. So